In this lesson, we're going to wrap up our look at the reactions of aldehydes and ketones, focusing on the acyl addition eliminations using amines as nucleophiles. Aldehydes and ketones can undergo acyl addition elimination with primary amines to give imines. As you can see in the example, an imine is a molecule with a carbon-nitrogen double bond. Imines are essentially the nitrogen analogs of carbonyls. In this example, acetone is reacted with methanamine under acidic conditions to give an imine and water as a byproduct. The reaction mechanism is a six-step acid-catalyzed acyl addition elimination. The first two steps involve the protonation of the carbonyl oxygen and nucleophilic attack of the amine onto the carbonyl carbon. The order of these first two steps is actually highly debated. Here, I show protonation of the carbonyl oxygen first, followed by the attack of the amine onto the carbonyl carbon. There is, however, evidence that suggests that the amine actually attacks the carbonyl first, and the resulting intermediate is protonated in the second step. My own belief is that each version of the reaction mechanism is likely correct. The order of the first two steps is likely dictated by both electronic and steric effects on the amine and the carbonyl. The order shown here, while likely less common, more closely aligns with the mechanisms of other acid-catalyzed reactions of carbonyls, making it easier to understand and remember. Regardless of the order of the first two steps, the third step is the deprotonation of the ammonium ion to give a geminal aminol. The fourth step is simply the protonation of the alcohol oxygen. In the fifth step, a lone pair on nitrogen forms a pi bond to the adjacent carbon, expelling water in the process. The final step is the deprotonation of the aminium ion to give the final imine product. Aldehydes and ketones can undergo acyl addition elimination with secondary amines to give enamines. As you can see in the example, an enamine is exactly what the name suggests, a compound that is both an alkene and an amine. Here we see acetone reacting with methylmethanamine under acidic conditions to give an enamine and water as a byproduct. The reaction mechanism is a six-step acid-catalyzed acyl addition elimination. Fortunately, the mechanism is nearly identical to the mechanism for the imine formation, differing only in the final step. The first two steps are the protonation of the carbonyl oxygen and nucleophilic attack of the amine onto the carbonyl carbon. As we saw for the mechanism of imine formation, the order of the first two steps is debated, and likely depends on the specific carbonyl and amine used. The next three steps are also identical to those in the imine formation. The ammonium intermediate is deprotonated to give a geminal aminol, and the oxygen protonated to give an alkoxonium ion. A lone pair on nitrogen forms a pi bond to the adjacent carbon, expelling water in the process. It's only in the last step that the reaction mechanism deviates from the mechanism for the imine formation. If you recall, the last step in the reaction mechanism for imine formation was the deprotonation of nitrogen. Because a secondary amine is used in the formation of an enamine, the aminium ion formed at this stage simply doesn't have a proton on nitrogen to remove. The aminium ion here is neutralized by the removal of an alpha proton, a hydrogen atom on an adjacent carbon. As the alpha proton is removed, electrons flow to create a new carbon-carbon pi bond, breaking the existing carbon-nitrogen pi bond, giving the final enamine product. The final reaction we'll explore is a reaction you've likely seen before, the Wolff-Kishner reduction. The Wolff-Kishner reduction is the deoxygenation of an aldehyde or a ketone using hydrazine under basic conditions. In the example, we see acetophenone undergoing Wolff-Kishner reduction to give ethylbenzene. If you look closely at the structure of hydrazine, you can see that it strongly resembles a primary amine. And we've seen that aldehydes and ketones react with primary amines to give imines. If we look at the reaction mechanism, we see that the reaction involves the formation of a special imine intermediate called a hydrazone. A proton is removed from the terminal nitrogen of the hydrazone using a strong base. The resulting resonance-stabilized anion is then protonated on carbon, forming a nitrogen-nitrogen pi bond in the process. The second proton is then removed from the terminal nitrogen, forming a nitrogen-nitrogen triple bond and breaking the existing carbon-nitrogen bond. This results in the formation of a carbanion and nitrogen gas. In the last step, the carbanion is protonated by a weak acid to give the final product.